So today we will start our, I would say, a very, very important topic where you have to apply model.fit. Mention your training set that you have, extract, building a scene and model. run this part. Let's see if we get any error or not. Architecture and how we are doing the implementation of this. Oh, very good evening to everyone. Can you guys just give me the confirmation whether I am clearly audible and results which we have done in our last discussion. So I'm waiting for a few seconds so that you guys will be ready. So what I was talking about, accuracy you can see over here. So this is the test accuracy, which is 98.49%, and this is the train accuracy, which is 99.64%. I will try to share the specific collab link as well. Yes, afterwards I told you that we will cover up. Now, how can we save this specific model which we have trained, and how we will be able to get the predictions of our model, right? Whether it is predicting correct or not. Also, I have given you the task, if you remember, of doing the calculation of the specific parameters. So I'm expecting that you guys have the specific parameters I'm talking about. You guys have done this. So just first of all, be ready with the file, and then maybe we can start our discussion. Just give me the confirmation once you're ready. All set. What about others? Can I get the same answer from everyone? And in the meantime, I will do one thing. I'll copy this snapshot over here. Set, all set for everyone? Shall I start now? Okay, perfect. So first of all, let's start our discussion with respect to how we will be able to evaluate these parameters and these output shape values, right? So anyone who can answer me that, first of all, let me write it over here. I hope you all know that in this specific model, the kernel size or the filter size was 3, 3 or 3 cross 3, right? And the number of filters that we have used, anyone can just let me know in the code how many number of filters we are using. I feel it was 32. Yes, it is 32. Okay. Now, what was the input shape of our data? That is also I'm writing it down over here. It was 28 cross 28 cross 1. 28 cross 28 is the size of the image, and when I'm saying cross 1, it indicates the number of channels. So because we are working with a grayscale image over here, so that is why I think in the last discussion I told you this specific result is 1. Now, can you just help me to understand that how is this 320 is coming up? So these parameters will be evaluated on the basis of exactly what is the, because that many number of computations will happen, right? So it all depends on how much is the dimension of filters. That many times the computations will happen. So it is nothing but what is the filter height, I would say, into what is the filter width, into how many number of channels you are working with for now. So in our case, input channel is only 1 because we are working with a grayscale image, plus the bias factor we always have to take care of. And now, in total, how many number of filters are doing the same computation? So we will be having 32 filters. Right? So that many number of parameters are working internally. So in our case, the 32 into filter height is 3, filter width is 3, input channel is 1, and whatever the input channel we have, that I would say that will be the kind of a bias also in our case. So bias is also 1. So if you will try to evaluate this, 3 into 3 is 9, 9 plus 1 is 10. So if you multiply this number, the answer you will be able to get is 320. So this is where we will be able to get the very first parameter in our convolutional 2D layer. Give me the confirmation if this is clear. Clear? Achha, who will tell me how we are getting the output shape as 26 cross 32? Just apply the formula which we have discussed, n minus that filter size plus 2p divided by s plus 1. And just check. What is the value of n? 28. What is the filter size? 3. What is the value of padding? For now I think it is 0. Stride is I think 1 plus 1. So 25 plus 1 is 26. It means this is the value of the output shape that we will be able to get. So 26 is the height and the width of the output shape into 1 because we're working with one channel, and because we're applying the same task for 32 filters, the output dimensions will become 26, 26, 32. This 32 last part indicates the count of filters. Because over here we don't have a single filter, we have 32 filters working internally. So that is where we will be able to get the specific shape. Is this clear to everyone? Shall we move further? Both the values, how we're getting the output shape and how we're getting the parameter value, both of them are clear. The first factor indicates as none because kind of it indicates the batch size. We are not working with batches for now. I hope you all remember the concept of batches. So for now we are not talking about that part, so we are taking it as a none, or by default it will be taken as a none. Shall we move ahead? So majorly the shape is this last 26, 26, 32. Now, max pooling we are applying as a 2D. So I hope you all remember, as soon as we are saying we are applying a max pooling of 2D, so automatically, whatever be the size of your dimensions output shape you have, you will be able to pick with respect to the 2 cross 2 matrix, that maximum value. So the size of the output shape is automatically get reduced by 2. So it will be 13 cross 32 as the output shape. Is this fine? And in this specific case, we don't have any trainable parameters. We are just trying to do the max pooling. We are not doing any filtration operation on top of that. So nothing we are doing over here. So we are just getting a shape as 13, 13, 32. Clear? Everyone is comfortable till so far? Shall we move to the third layer that we have created? Flattening layer. Can I get the confirmation from everyone before I'll move ahead? I want the confirmation. That whether these two things are clear, these two rules are clear or not. Again, for those people who were not there with me in the last class, directly have joined this specific session, I will request them to leave the class as soon as possible, because I don't think you will be able to get the idea, because this is kind of a continuation of previous class itself, right? Explain max pooling once. I have explained, I think in the last class as well, but because you're asking, let me explain you again. So for example, max pooling is a very simple concept which says that, let's say you will be having an output image size as 4 cross 4, which you can see on my screen, right? This is the output image size. Now you are saying that I will apply all here and big term. There will be simple ones for to of, right? 2 crucial is start with part In max pooling, we just have to make sure we are not leaving any single value in terms of rows and columns. और किसी भी specific value को double भी नहीं लेना. We don't want to inculcate any specific value 2 times. So once we will be able to compare 12, 20, 8 and 12, I don't want to include 20 and 12 again, like this. Because that doesn't make sense. In that case, maybe, so that will cost by creating it and doing the step-by-step implementation in the scribble link, then the entire session of mine in today's class will be gone over there. That's the main idea. So if you really want to analyze this, maybe after the session will get over, you can just maybe refer any of the chat GPT or any of the LLM based tool and tell them to create the image for this, and they will definitely be able to create it within few minutes, and then you can analyze the same. Right? Now, in the next third part, we have tried to create the flattening layer. Now, in the flattening layer, how many number of values as the input values we will be having? We will be able to have 5408. How we will get the answer? It's very simple. If you remember, what was the flattening layer? The things that we will be having in a matrix, now we are converting it back to the one dimension. So it will be nothing but 13 into 13 into 32. So if you will try to compute 13 into 13 into 32, I'm pretty sure you will be able to get the answer as 5408. Just try it out and confirm to me, is that correct or not? Just try it out and let me know, is that correct or not? I have not done it. Maybe you can just use the calculator and confirm to me before we will proceed ahead. Is it correct? Perfect. So till so far our understanding is fine. So now we will be having a convolutional layer, then a max pooling layer, then a flattening layer. Now we are somehow shifting towards the other concept of implementing a neural network. Is this correct? Be having a very huge amount of data. We work with batches, right? It can be, we are saying that in one iteration, maybe 10 samples should go and do the working internally simultaneously. So that is where batch size is something which we have to define. Currently, we are not doing anything in batches. Here we are taking one by one all the images. So that is where the value is none by default in every case. Is that clear? So for now, don't focus more on it. Once we will start working with the batches, then I will showcase you the values will get changed, and then you will get more sense. For now, the last three numbers, that the values which you are observing, focus over there, that how we are getting those values for now. Now, next step is where we will be having a dense layer, kind of a hidden layer, where we will be having the number of neurons as 128. Now, anyone who can give me the answer, how we are getting these many parameters? I hope you all remember the formula which we usually cover up. How many number of input neurons we have? How many number of input neurons we have? This is 5408. Yes, everyone? Now, plus, we do have a bias. Into, how many number of output neurons we have? How many number of output neurons we have? How it will be 13, 128, right? This is input layer will be having 5408 as the input values. One bias will be there. And as an output, there are 128 neurons available. Yes or no, everyone? Solve this value and let me know whether this is equal to the answer which is mentioned over here. 692352. Can you implement 5409? 5409 into, what was the value? 128, right? 69 2352. Exactly. It is absolutely correct. Getting my point? Yes or no? Now, for the last layer, what are the how many number of input neurons we have? For the last layer, how many number of input neurons we have? 128. Bias? Will all shell part. Okay, one very simple to sort of load that specific train, save extension to save it, right? And once you will run the specific step, let's see what will happen. Uh, my file got disconnected. I'm not sure why. This specific model. Now, what we usually do, whenever, let's say you are working in any project, we usually give this specific H5 file to the clients, right? For whatever clients you're working with. So you don't usually share the entire code. This is the file. This H5 file contains the entire model summary with respect to whatever work you have done. And at any point of time, if your clients also wants to see the predictions, they can just have this file. They will directly load this file and check the predictions at any point of time. So it's kind of a easier way to, I would say, communicate between different clients and even in among different team members rather than showcasing the entire code to them. So no one usually showcase their entire code. They just try to share the files, which is the model saving file with them. So let me try to do one thing. What is the best habit is always have a backup file with respect to whatever work you are doing. So just download this file because we're also working in a collab environment. So what we can do, maybe I have a folder. If you are also having a separate folder with respect to whatever work you are doing, you can just save it over there. I am also saving it in today's folder, and within few minutes, my file will get saved, which I can definitely share with you after the session will get over. But this is the file which I will be able to save it now. Shall we move ahead? Just open. So first button, wherever your file is, what to load, you 5 files. Import flow, we need to model. Shell to can the more user. sample image and we may capture that specific sample image. That whether we will print under at the very end in the given model, what is the activation function of out? I will pass, it will print to me. So I will pass all the predictions to this specific be able to, I am to check out talking about few minutes. So but input shape should always be same. Now how can we make it same? That is where I will try to use one function called as expand. So input underscore image will be equal to np dot expand dimensions. So it will try to expand this to image looks like is, let me, this is predictions, predict which as the next, maybe I think the probability of each and every class. For example, class 0, this is the probability. Class 1, this is the probability. Class, that's one probability. And otherwise, you're testing on a different, right? Yes, yes, 4 can win. Now, max, prints, and that is have a, see how we, let try to print how our occupable image looks like. To input image looks the image available with us. how our sample image do have doing the like. Yes, we do have something over here as well. Let me try to print how our input image looks like. Define sections. Let's change what we do have something over here as well. Okay. Let me try to print how our input image looks like. I want. Have I changed? I think now we are getting the probability of each and of this one are effects in that making really this book quiz class. Comfort. Comfortable till so far? Let's try to showcase you one more interesting thing we can understand as a team. Can you see this? So our sample image by default shape was in the testing set. In the test set, the sample image which we are grabbing, the very first image, the shape is 28, 28, 1. If you will be able to observe, I have tried to use the function called as expand dims. So automatically you will be able to understand that it will somehow try to expand the dimensions of the specific input image. How it will expand? I have mentioned the parameter x is equal to 0. So if you remember in our previous discussion when I was explaining you this specific concept, I told you that there are 4 parameters, 1, 2, 3, 4. By default, this first parameter will come always, which indicates the count of the batch size. You remember that? Now, when we are passing our input image to our same model, which contains this as the very first parameter, so we have to make sure that our input image will also go in the form of 4 parameters rather than 3 parameters. So what I have done, I have mentioned that my batch size is initially 1 because at a time, currently I am passing only single image, and after that, take the dimensions as it is, 28, 28, 1. So what will happen in this specific case, we are passing this specific input image. And that is why when you are taking the dimensions of input image, you will be able to get this specific dimensions. So that is the only change that we have made. After that, once it is done, we will be able to get the predictions pretty well. So this is the which specific step we have done over here. Step number 6 is loading the model. Then this is the step number 7, where we are making the predictions. So model, predictions. Can we take actual output? So whatever step I have to do next, you guys already told me. That's the beauty about this class. I have to teach you this as the next step number 8. Have patience. Till so far everything is clear. Can I get the confirmation? Any doubt? Doubt till so far were used in prediction. Is it clear? So, in future, whenever you want to make the predictions, you don't need to rerun the code again. Just upload your file of H5, load your file. I have already showcased you how will you load. Sample in one title, predicted out, right? In the image itself, you can say predicted class or predicted output, and here you can mention predicts class, and you will be asking use the reshape part to TA who said in our last class or in the chat window. Is this clear to everyone? Priyanshi is asking one question over here that we word who's what is this class? You guys size is it? I really want you guys this one in kind this one in guys all she had up. Please say underscore image x test. Try to rejoin the session or check your internet is visible. Part of can talk about the very first time internally us we have available with us responsible of doing different tasks. AlexNet is one of them and is quite famous. Now, if you want to explore on your own about the architecture of any of the convolutional based neural network, I think now after the today's discussion, you are ready to explore and try to see that how the different neural networks looks like, architectures looks like at your end as well. What you're supposed to do, for example, let's say you want to explore about AlexNet architecture. So the better idea will be where you will be able to download the research paper. So you will be able to see this is the research paper that we will be having. And when you are starting your journey to, I would say, understand about these convolutional neural networks, once you will be able to get the understanding in this specific session, try to read line by line the research paper. In the research paper, try to understand the abstract part very carefully, which is a very, very important thing. After that, the introduction part, where we're talking in the image resolution images, 1,000 images in each of the 1,000 categories. So basically, at the end of the day, Max is AlexNet. It might seem a bit difficult to you that, hey, there are so many things we are having in this specific architecture. And in almost all the famous architectures which you will be able to see, architecture might seem a bit difficult to you to understand. But maybe I will try to showcase you step by step how the AlexNet architecture is working internally. That will help you to get an idea that how basically we should be able to get the understanding of how this architecture. 1000, which clearly told you it asks to insert one image, and so ask having 1000 labels, 1000 classes with them. So how this architecture looks like, let me try to insert one image and we'll try to explain you step by step. So this is the architecture of LXNet. I hope everyone can see on my screen this specific architecture. This is more beautiful as comparable to what you can see in the research paper. In the research papers, usually the kind of architecture we have is bit black and white, and that's why people usually get worried that, hey, it's very difficult, it's not understandable at all. So at that point of time, you can refer any other images available on Google itself, and you will be able to find out. Now, I have find out this specific architecture bit more easy to understand and to make you guys understand. That's why I'm picking up this one. But every architecture of LXNet will look exactly same. Okay? Now, whatever be the numbers which you are seeing over here, the input shape, the kernel size, number of kernels or the filters, stride value, pooling value, or padding value, all of these things are the experimentation value which the researchers have done to get the maximum accuracy at the end of the day, to classify the ImageNet based data on the 1000 classes that they will be having. So who are those people? You can also search on the research paper. I think in the starting of the research paper, usually you will find the researcher's name very easily. So I hope everyone knows about him, Jeffrey Hinton. He has done a lot of amazing job, in the field of deep learning. You will find his name in maximum research papers with respect to what we will be able to cover up in the upcoming sessions as well. One of the most common name, and even there are few of the PhD scholars under him. You will find their name as well quite frequently in multiple works of deep learning architectures. Apart from this, everyone is from University of Toronto, and here you can see Alex and Alia. These might be, I'm not really sure, might be their team members or their students, not really sure, but these are the three people who have done this specific research work and come up with this specific architecture. Now, how this architecture works, let's try to understand it step by step. So what they have done is, if you will be able to see the data set very carefully, you will find that this data, I think in this research paper also they must have mentioned somewhere 7 with it, and it's a RGB based channel, it's a RGB image, so it will come as cross 3. So this is the input shape where they started their journey. Is this clear to everyone? Yes or no? Is this clear? Shall we move ahead? You have to stop me at any point of time wherever you feel it's not clear, because it's the very first architecture, standard architecture which we are discussing today. is, we have discussed CNN. The name is different, but this is also a CNN architecture. In the CNN architecture, we are dealing with images. Now, image can be of two types. It can be grayscale. It can be RGB. Grayscale example, few minutes back we have seen in MNIST data, which contains numbers or images in a grayscale manner of size 28, 20. Today we are, and in the ImageNet based data, so both of them are applying a CNN strategy, same what we have covered up. It's just the data set is different. Is this clear to everyone? Any doubt over here? Shivam, is this clear to you, what I'm trying to convey? So you always have to remember what we have covered up in our CNN architecture, because same on input images we will be applying a filter, and then it will be able to generate the output image. So now if you will see this very carefully, we have this input image. They're applying a kernel size of 11 cross 11. So because the image size is very, very big, so if we will be applying a 3 cross 3 kernel, it will be lot of computations. So what they have done is they have increased the kernel size, filter size to 11 cross 11. And again, to make the computation bit faster, they have increased the stride value to 4. So listen it very carefully. Kernel size, they have used 11 cross 11. When I'm saying they have used, those 3 people who have done the complete research of this architecture. Stride value is 4. And the count of total number of kernels or the filters are 96 to make the training much, much faster. So if this is the criteria, what do you think is the expected output image? If I'll ask you this question, that, hey, I'm providing you an input shape as 227 cross 227, and it's a RGB image, so consider it as 3. Kernel size as 11 cross 11, and the count of the kernels 96. So all those 96 kernels have 11 cross 11 dimension. Stride value is 4, and because I'm not providing you a padding for now, it will be 0. So can you just let me know what is the expected output shape after applying a convolutional strategy on top of this? When I'm saying convolutional strategy, I hope you all remember, filter will be mapped on top of the input image, multiplication and addition will happen, and we will be able to get the final values of the output image. So what are the dimensions of the output shape? Will you 11, 0? So I it comma, anyone 6 is coming up? Anyone who can just let me know? How is this 96 is coming up? Number of kernels. See, I hope you understand this point now. How they will be able to achieve this output 55, 55, 96. Tell me yes or no. Just give me answer straightly, yes or no. Clear? I am explaining you today one architecture. I will give you a task to understand about the other architecture on your own at your end once the session will get over. So you have to do it like this only, where you are saying kernel is basically used 96 kernels of dimensions 11 cross 11. So at the final end, we will be having those 96 filters available with us, and the output shape will get changed because 11 divided over here. Clear? Everyone? Before this, we didn't consider for output only shape. Before this, if you remember in our previous discussion of MNIST data, we have taken 32 count of filters. So if you will be able to see in the output shape, we're getting the answer as 32. 26, 26, 32. Do you remember? समझ में आया कि नहीं आया? Same thing they are doing.
World like this, AlexNet, was published in 2012 in an 8-page paper that shocked the computer vision community by showing that an old AI idea would work unbelievably well when scaled. The paper's second author, Ilya Sutskever, would go on to co-found OpenAI, where he and the OpenAI team would massively scale up this idea again to create ChatGPT. This video is sponsored by KiwiCo. More on them later. If you look under the hood of ChatGPT, you won't find any obvious signs of intelligence. Instead, you'll find layer after layer of compute blocks called transformers. This is what the T in GPT stands for. Each transformer performs a set of fixed matrix operations on an input matrix of data, and typically returns an output matrix of the same size. To figure out what it's going to say next, ChatGPT breaks apart what you ask it into words and word fragments, maps each of these to a vector, and stacks all of these vectors together into a matrix. This matrix is then passed into the first transformer block, which returns a new matrix of the same size. This operation is then repeated again and again, 96 times in ChatGPT 3.5 and reportedly 120 times in ChatGPT 4. Now, here's the absurd part. With a few caveats, the next word or word fragment that ChatGPT says back to you is literally just the last column of its final output matrix, mapped from a vector back to text. To formulate a full response, this new word or word fragment is appended to the end of the original output, and this new slightly longer text is fed back into the input of ChatGPT. This process is repeated again and again, with one new column added to the input matrix each time, until the model's output returns a special stop word fragment. And that is it. One matrix multiply after another, ChatGPT slowly morphs the input you give it into the output it returns. ChatGPT slowly morphs the input you give it into the output it returns. Where is the intelligence? How is it that these 100 or so blocks of dumb compute are able to write essays, translate language, summarize books, solve math problems, explain complex concepts, or even write the next line of this script?
The answer lies in the vast amounts of data these models are trained on.
Okay, pretty good, but not quite what I wanted to say next. The AlexNet paper is significant because it marks the first time we really see layers of compute blocks like this learning to do unbelievable things. An AI tipping point towards high performance and scale and away from explainability. While ChatGPT is trained to predict the next word fragment given some text, AlexNet is trained to predict a label given an image. The input image to AlexNet is represented as a three-dimensional matrix or tensor of RGB intensity values, and the output is a single vector of length 1000, where each entry corresponds to AlexNet's predicted probability that the input image belongs to one of the 1000 classes in the ImageNet dataset. Things like tabby cats, German shepherds, hot dogs, toasters, and aircraft carriers. Just like ChatGPT today, AlexNet was somehow magically able to map the inputs we give it into the outputs we wanted, using layer after layer of compute block, after training on a large dataset. One nice thing about vision models, however, is that it's easier to poke around under the hood and get some idea of what the model has learned. One of the first under-the-hood insights that Krzyzewski, Sutskever, and Hinton show in the AlexNet paper is that the model has learned some very interesting visual patterns in its first layer. The first 5 layers of AlexNet are all convolutional blocks, first developed in the late 1980s to classify handwritten digits, and can be understood as a special case of the transformer blocks in ChatGPT and other large language models. In convolutional blocks, the input image tensor is transformed by sliding a much smaller tensor called a kernel of learned weight values across the image, and at each location computing the dot product between the image and kernel. Here, it's helpful to think of the dot product as a similarity score. The more similar a given patch of the image and kernel are, the higher the resulting dot product will be. AlexNet uses 96 individual kernels in its first layer, each of dimension 11 by 11 by 3. So conveniently, we can visualize them as little RGB images. These images give us a nice idea of how the first layer of AlexNet sees the image. The upper kernels in this figure show where AlexNet has clearly learned to detect edges, or rapid changes from light to dark at various angles. Images with similar patterns will generate high dot products with these kernels. Below, we see where AlexNet has learned to detect blobs of various colors. These kernels are all initialized as random numbers, and the patterns we're looking at are completely learned from data. Sliding each of our 96 kernels over the input image and computing the dot product at each location produces a new set of 96 matrices, sometimes called activation maps. Conveniently, we can view these as images as well. The activation maps show us which parts of an image, if any, match a given kernel well. If I hold up something visually similar to a given kernel, we see high activation in that part of the activation map. Notice that it goes away when I rotate the pattern by 90 degrees. The image and kernel are no longer aligned. You can also see various activation maps picking up edges and other low-level features in our image. Of course, finding edges and color blobs in images is still hugely removed from recognizing complex concepts like German shepherds or aircraft carriers. What's astounding about deep neural networks like AlexNet and ChatGPT is that from here, all we do is repeat the same operation again, just with a different set of learned weights. For AlexNet, this means that these 96 activation maps are stacked together into a tensor that become the input to the exact same type of convolutional compute block, the second overall layer in the model. We can make our activations easier to see by removing the values close to 0. Unfortunately, in our second layer, we can't learn much by simply visualizing the weight values in the kernels themselves. The first issue is that we just can't see enough colors. The depth of the kernel has to match the depth of the incoming data. In the first layer of AlexNet, the depth of the incoming data is just 3, because the model takes in color images with red, green, and blue color channels. However, since the first layer computes 96 separate activation maps, the computation in the second layer of AlexNet is like processing images with 96 separate color channels. The second factor that makes what's happening in the second layer of AlexNet more difficult to visualize is that the dot products are really taking weighted combinations of the computations in the first layer. We need some way to visualize how the layers are working together. A simple way to see what's going on is to try to find parts of various images that strongly activate the outputs of the second layer. For example, this activation map appears to be putting together edge detectors to form basic corners. Remarkably, as we move deeper into AlexNet, strong activations correspond to higher and higher level concepts. By the time we reach the 5th layer, we have activation maps that respond very strongly to faces and other high-level concepts. And what's incredible here is that no one explicitly told AlexNet what a face is. All AlexNet had to learn from were the images and labels in the ImageNet dataset, which does not contain a person or a face class. AlexNet was able to learn completely on its own, both that faces are important and how to recognize them. To better understand what a given kernel in AlexNet has learned, we can also look at the examples in the training dataset that give the highest activation values for that kernel. For our face kernel, not surprisingly, we find examples that contain people. Finally, there's this really interesting technique called feature visualization, where we can generate synthetic images that are optimized to maximize a given activation. These synthetic images give us another way to see what a specific activation layer is looking for. By the time we reach the final layer of AlexNet, our image has been processed into a vector of length 4096. The final layer performs one last matrix computation on this vector to create a final output vector of length 1000, with one entry for each of the classes in the ImageNet dataset. Krzyzewski, Sutskever, and Hinton noticed that this second-to-last layer vector demonstrated some very interesting properties. One way to think about this vector is as a point in 4096 dimensional space. Each image we pass into the model is effectively mapped to a point in this space. All we have to do is just stop one layer early and grab this vector. Just as we can measure the distance between 2 points in 2D space, we can also measure the distance between points or images in this high-dimensional space. Hinton's team ran a simple experiment where they took a test image in the ImageNet dataset, computed its corresponding vector, and then searched for the other images in the ImageNet dataset that were closest, or the nearest neighbors, to the test image in this high-dimensional space. Remarkably, the nearest neighbor images showed highly similar concepts to the test images. In Figure 4 from the AlexNet paper, we see an example where an elephant test image yields nearest neighbors that are all elephants. What's interesting here too is that the pixel values themselves between these images are very different. AlexNet really has learned high-dimensional representations of data where similar concepts are physically close. This high-dimensional space is often called a latent or embedding space. In the years following the AlexNet paper, it was shown that not only distance but directionality in some of these embedding spaces is meaningful. The demos you see where faces are age or gender shifted often work by first mapping an image to a vector in an embedding space, and then literally moving this point in the age or gender direction in that embedding space, and then mapping the modified vector back to an image. Before we get into activation atlases, which give us an amazing way to visualize these embedding spaces, please take a moment to consider if this video's sponsor is something that you or someone in your life would enjoy. I was genuinely really excited to work with this company. They make incredibly thoughtful educational gifts. Pencil sharpener from the Eureka Crate line, which is focused on science and engineering. It includes these special crayons specifically designed to help her learn different ways of graphing off your first month of a subscription. Synthetic images that maximize a given set of activations, with a two-dimensional projection or flattening out of the embedding space, to make these incredible visualizations called activation atlases. Neighbors on the activation atlas are generally close in the embedding space, and show similar concepts the model has learned. We're getting a peek into how deep neural networks organize the visual world. Looking at the synthetic images that most activate neighborhoods of neurons, we can visually walk through the embedding space of the model, seeing it make smooth visual transitions from concepts like zebras to tigers to leopards to rabbits. Moving to the middle layers of the model, we can see less fully formed but still meaningful concepts. Moving along this path amazingly correlates with the number and size of pieces of fruit in an image. The same principle applies in large language models. Words and word fragments are mapped to vectors in an embedding space, where words with similar meanings are close to each other, and the directions in the embedding space are sometimes semantically meaningful. There's some incredible, very recent work from the team at Anthropic that shows how sets of activations can be mapped to concepts in language. These results can help us better understand how LLMs work, and can be used to modify model behavior. After clamping a set of activations that correspond to the concept Golden Gate Bridge to a high value, the LLM the team was experimenting with began to identify itself as the Golden Gate Bridge. AlexNet won the ImageNet Large-Scale Visual Recognition Challenge by a wide margin in 2012, the third year the challenge was run. In prior years, the winning teams used approaches that under the hood look much more like what you might expect to find in an intelligent system. The 2011 winner used a complex set of very different algorithms, starting with an algorithm called SIFT, which is composed of specialized image analysis techniques, developed by experts over many years of research. AlexNet, in contrast, is an implementation of a much older AI idea, an artificial neural network, where the behavior of the algorithm is almost entirely learned from data. The dot product operation between the data and a set of weights was originally proposed by McCulloch and Pitts in the 1940s, as a dramatically oversimplified model of the neurons in our brain. In the second half of each transformer block in ChatGPT, and at the end of AlexNet, you'll find a multi-layer perceptron. The perceptron is a learning algorithm and physical machine from the 1950s that uses McCulloch and Pitts neurons and can learn to perform basic shape recognition tasks. Back in the 1980s, a younger Jeff Hinton and his collaborators at Carnegie Mellon showed how to train multiple layers of these perceptrons using a multivariate calculus technique called backpropagation. These models were a couple layers deep and remarkably pretty good at driving cars. In the 1990s, Jan LeCun, now chief AI scientist at Meta, was able to train 5-layer deep models to recognize handwritten digits. Despite the intermittent successes of artificial neural networks over the years, this approach was hardly the accepted way to do AI, right up until the publication of AlexNet. If this was obviously the way to build intelligent systems, we would have done it decades earlier. As Ian Goodfellow writes in his excellent deep learning book, At this point, deep networks were generally believed to be very difficult to train. We now know that algorithms that have existed since the 1980s work quite well, but this was not apparent circa 2006. The issue is perhaps simply that these algorithms were too computationally costly to allow much experimentation with the hardware available at the time. The key difference in 2012 was simply scale of data and scale of compute. The ImageNet dataset was the largest labeled dataset of its kind to date, with over 1.3 million images. And thanks to NVIDIA GPUs, in 2012, Hinton's team had access to roughly 10,000 times more compute power than Yann LeCun had 15 years before. LeCun's LaNet 5 model had around 60,000 learnable parameters. AlexNet increased this 1,000-fold to around 60 million parameters. Today, ChatGPT has well over 1 trillion parameters, making it over 10,000 times larger than AlexNet. This mind-boggling scale is the hallmark of this third wave of AI we find ourselves in today, driving both the performance and the fundamental difficulty in understanding how these models are able to do what they do. It's amazing that we can figure out that AlexNet learns representations of faces, and that large language models learn representations of concepts like the Golden Gate Bridge. But there are many, many more concepts these models learn that we don't even have words for. Activation atlases are beautiful and fascinating, but very low dimensional projections of very high dimensional spaces, where our spatial reasoning abilities often fall apart. It's notoriously difficult to predict where AI will go next. Almost no one expected the neural networks of the 80s and 90s, scaled up by 3 or 4 orders of magnitude, to yield AlexNet. And it was almost impossible to predict that a generalization of the compute blocks in AlexNet, scaled up by 4 orders of magnitude, would yield ChatGPT. Maybe the next AI breakthrough is just another 3 to 4 orders of magnitude of scale away. Or maybe some mostly forgotten approach to AI will resurface, as AlexNet did in 2012. We'll have to wait and see. Are you mad that I called the blocks of compute dumb?
Not at all. Describing the compute blocks as dumb highlights the impressive nature of how simple operations can combine to produce intelligent behavior. It's a great way to emphasize the power of the underlying algorithms and training data.
In today's video, I want to talk about AlexNet. I've been rereading the seminal paper by Alex Krivzewski, and I found that there were many small interesting bits. If we rewind back to before 2012, most datasets for computer vision were small and specialized. For instance, the NORB dataset contains only 50 toys image. During that time, as compute resources became cheaper, models with higher capacity become trainable. This incentivized people to create bigger datasets like LabelMe and ImageNet. So LabelMe is a community-contributed dataset coupled with an open annotation tool. So ImageNet is a huge set of images arranged in a structured hierarchy, following the WordNet hierarchy, crowdsourced on Amazon Mechanical Turk. So having dataset that big require a model with large capacities like deep neural network, and convolutional neural network are especially well suited for this image recognition task because of the assumption built in the network that resemble kind of the visual system of the human brain. If we take a closer look at ImageNet, we see that it has in total 15 million images with label. This was an enormous amount at the time. We can see here that the hierarchy I was talking about earlier. So on the top we have mammal, and then placental, and then carnivore, canine, dog, working dog, and then finally husky. Same thing for vehicle down there until Chimaran. With the dataset, there is an annual competition called ImageNet Large Scale Visual Recognition Challenge that happen every year. So the year that AlexNet won the competition, we can see that there was a significant gain provided by the network and the methodology that Alex and Jeff Hinton used. So this is almost like 10% reduction in error. So although the image themselves are high resolution, they were reduced to a fixed 256 x 256 pixel resolution in order to reduce the size required for the network. So let's take a look at the architecture now. Here is the figure from the paper with some annotation. It's a bit weird and very loaded, so we'll step through it slowly. The picture seems cut at the top, but strangely enough, this is how it was in the original paper. The first thing to note is that the activation function they used was a ReLU instead of the sigmoid or Tanesh that were commonly in use. So ReLU was used throughout the network. So ReLU looked like the image on the left. It's a very simple function that is differentiable everywhere except at 0. The rationale for using this kind of activation function is that they learn faster than sigmoid or Tanesh function. So on the right, you can see that there's two lines. The solid line is the training error of the ReLU function, a network using ReLU function across epoch, and then the dashed line is damage. And we can see that the ReLU is like 6 times faster for this network, and in general it's way faster. So one novel thing the author did at the time was that they train on multiple GPUs, so here too, in order to increase the size of the network. So the GPU at the time had 3 GB of memory, so this was kind of a limiting factor for the size of the network. So they used 2 of them, and this is why you see that the network is kind of split in 2. So another net trick that they use that is biologically inspired is to use the local response normalization, also called brightness normalization. So this is a process that is similar to what is happening in the retina. If you want to learn more about it, I did a full video on that because it's super interesting. So AlexNet has another particularity. It used overlapping pooling instead of the traditional non-overlapping pooling for the convolution. So overlapping pooling is like having like overlapping receptive field across neuron, as shown at the bottom of this picture. They find that this method could reduce error rate by about 0.3 to 0.4%. They also report less overfitting with this strategy. So let's look back at the architecture, knowing the previous information. So the first thing to note here is that some layers are in GPU 1 and some layers are in GPU 2. There are also like inter-GPU connection at specific point and intra-GPU connection at others. So this is like a very, very specifically wired network. So the input layer here is a 224 by 224. This is a bit odd since we've stated that they shrank the image to be 256, but this is due by the data augmentation scheme they used, which we'll see in a few. So the first 5 layers are all convolution layer. Last 3 are fully connected feed-forward layer, ending with 1,000 ways softmax because there are 1,000 categories in the subset of ImageNet that they used. So the connection intra-GPU are constrained to layer 2, 4, and 5, so those are within the convolution layer. And in the paper they show that because of this, the GPU 1 and GPU 2 are learning different representation. I believe that one of them is more attuned to colors, and the other one is kind of color free. So the inter-GPU connection are in the 3rd covenant layer and in the fully connected layer at the end completely. So layer 3 is doing a lot of information passing across GPU, and after that in the fully connected layer they are pulling everything together. So like in the retina, a response normalization happens only in the first layers after the input has entered the system. So in this case it's layer 1 and 2, and I found it quite interesting that they kept kind of this this fact in the architecture. So here the max pooling that you see is the overlapping max pooling that they did. It happened at layer 2, 3, and 6. So an interesting thing to keep in mind here is that this network wasn't originally made with a well-maintained neural network library like PyTorch or TensorFlow. It's mostly custom C that Alex has worked on specifically for this network. It's pretty impressive because of the way the connections are made across GPU. And in the paper you can see that there's a link to the C++ code. I'm going to put it in the description. It's kind of nice to see. So the other used additional trick in order to avoid that their network overfit the data, because if you don't do these tricks, this network will overfit. So the first one is to use data augmentation with translation and horizontal reflection, like we see in the cat image down there. The second one is a bit weird. Is to alter the image pixel intensity by using PCA. So they did PCA on the whole ImageNet training dataset. And then what they do is they add multi-Gaussian distribution. So this is the alpha that you identity. So this way they could augment the dataset, but they also varied the intensity to remove this information for the network as a cheap way of kind of doing Ansible training in deep neural network. So what you do is every neuron except the input have a 0.5% chance of getting shut down, so that they're not doing anything for this round of training. So this is as if you're training a multiple network. So if you see here, we have a fully connected neural network in A, and then we do dropout. So we have a sparser network in B, and then we train for some batch, and then we redo it. So another set of neuron will be killed out. This reduces the interdependence between the neuron and make the network as a whole a bit more flexible. So this is important. Without this trick, the network will overfit badly. Finally, they train using a batch stochastic gradient descent optimizer with momentum. So you can check out my video on the subject where I go through the formula and I code sounding, coding in SIFT plus FV with the CNN made by Alex. The top one mean that you get the label exactly right. So it's the label with the most probable, with the highest probability, most probability. The Alex option time they didn't have the test results yet, so they used the validation set as a benchmark, and they said that at point like 8%, you have 5 CNNs. They also tried using Ansible one release, which is very good, which are very interesting. So if we look on the left panel, we can see that the 5 top label for each image, and some of very images they would, but they all make sense. So for example, the mite on top right, top left, it said mite, black widow, cockroach, tick, starfish. They kind of all make sense. So it seems that the network actually is learning a deeper representation. So if we look at the right panel, we see the image that leads to the most similar feature activation on the last fully connected layer. So they look at the activation of the neuron on the last layer to know if the image shown on. So that's it for today. We just have overfit and
just import models as well. Let me check. I think I've added to add. So here you can see directly output and let me know this is SNET today ask and the parameters and try to
Không là cái này không phải để là mình chỉ biết chỉ thầy chuẩn là mình đang chỉ đi thôi. Thật như thế nào thì thực giống như là sẽ có một cái mà chuẩn hay là cái guideline mà theo thôi. Thật không đúng nhá. Đây là sao thì như nào còn cái xem là như sao gọi là đạt thì lấy cái trang là chung cho nên thì lại có là như vậy guideline nó rất nhiều những cái sự nói như thế và cái để làm cái đấy thì nó là nó chỉ là cái mình rất mình thì biết là làm thế hiểu không cái mặt này của em đáp ngoan bạn thì kêu này và mình quên được mình có thể là mình để 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 có thêm một and
Mà em đâm mình cái bao không không nghe là đâu mà có bài đâu chả bài thì thế nào gọi là chỉ mé mé cho Hà Nội thôi của cái kiện này tắt ở đâu cái này cái đâu không thấy được nó cái an rồi vừa luôn Mình chụp việc cho em ra theo mình đến chứ cái biết what everything else. Wait.
you.